Hello, welcome to this lecture on modeling, analysis and estimation of three-phase unbalanced power network. So far we have been talking about the Y-bus matrix development and as well as the power flow equations. And then in the last lecture we have talked about the necessity of the representation of the internal buses for a generator, and we have also talked about the known quantities as well as the unknown quantities. So then therefore today in this lecture we are going to consolidate everything in a common framework. So to do that, let us take a small example. So let's say on 5 bus example, 5 bus example, just as an example. So then after we do understand this, then of course we can always generalize it for any system. So what we have is, we have got, let's say, a 5 bus system. So this is, and let's say that these are the buses and these are the lines. So these are the bus, so these are the bus. So let's say this is bus 1, bus 2, bus 3, bus 4, bus 5, and let's assume that I have got generators, 3 generators. One is connected at bus 1, one is connected at bus 2, one is connected at bus 3. So there are 3 generators, and here of course, and bus 5 and bus 4, these are all load buses. Please note, all these buses are actually unbalanced bus and all these lines are unbalanced lines. So then therefore every line is being represented by its equivalent pi model, and where this pi model is essentially being represented as, so if I have got bus I and j, so this pi model, that it is basically a 3 cross 3 matrix, and then this is also a 3 cross 3 matrix, and this is also a 3 cross 3 matrix. So every line is represented by an equivalent 3 cross 3 matrix pi model, which actually uses this 3 cross 3 matrices. So every line is essentially being represented by its equivalent 3 cross 3 impedance matrix, series impedance matrix, along with the 2 3 cross 3 shunt admittance matrix at its two sides. And every bus, also let's say bus 4 and 5, they have got loads, and essentially they have got loads at bus in actually phase A, phase B and phase C. So for example, in bus 4, the loads are PL 4A, PL 4B, PL 4C. Now because I have got 3 generators, so then therefore these 3 generators will have their internal bus. So then therefore this system will be augmented to, so this system would be augmented as this system. So bus, so initial buses are already there. So bus 1, bus 2, bus 3, bus 4, bus 5. So and then I will have, so these are the original lines. So this is bus 1, this is bus 2, this is bus 3, and this is bus 4, this is bus 5, and then the internal matrix. Let's say that this is bus 6, the internal matrix for bus 2 is bus 7, sorry, internal bus, and the internal bus for generator at bus 3 is 8, and there would be some impedance matrix here. These also impedance matrix, 3 cross 3 impedance matrix. There would be another 3 cross 3 impedance matrix, and there would be another 3 cross 3 impedance matrix. Now what is this impedance matrix that we need to discuss? Now so then therefore my original system size was n is equal to 5, m is equal to 3, where n is the number of buses in the original system. And m is number of generators. So now, so then therefore, now because of the fact that each of these three generator buses has got their own internal bus, so then therefore the effective number of buses in the augmented system is, so the number of buses in the augmented system is 8. So that is 5 plus 3. 5 is essentially the original number of buses, and this 3 is actually the internal buses belonging to each and every generator. So then therefore, for any general system having n number of buses and let us say m number of generators, the size of the augmented system would be n plus m. So n plus m is the total number of bus in the augmented system. For example, here n is equal to 5, m is equal to 3, so then it is 8. So then therefore, if there is any general system in which there are n number of buses and m number of generators, then that particular system also would be augmented by m number of internal buses. So then therefore, the ultimately the total number of buses in the system would be n plus m. Now what are these matrices? Now these matrices are nothing but the, we should say that these are generator impedance matrix. I should say that generator impedance matrix. So I can say that, so then let us say that this is GIM, generator impedance matrix. So this is also generator impedance matrix, this is also generator impedance matrix. So how do I get this generator impedance matrix? The idea is simple, that usually for every generator, the zero sequence impedance, positive sequence impedance and negative sequence impedance are known, right? So this is, so these are sequence impedance. These are sequence impedances of the generator which are generally known. From this sequence impedance, if we put these sequence impedances in a matrix in which these three values would be put into the diagonal. So, for example, if I now create a matrix Z0, Z1, Z2, this is 0, this is 0. So, this is a 3 cross 3 diagonal matrix, 3 cross 3 diagonal matrix. So, I construct a 3 cross 3 diagonal matrix by using these three values Z0, Z1, Z2, and then from this diagonal matrix then we will do the inverse transform in the ABC domain. So, then by doing inverse sequence transform, or rather instead of saying inverse sequence transform, this is a little confusing term. We should say that sequence to ABC transform. We should say that this is sequence to ABC transform, sequence to ABC transform. We get a 3 cross 3 matrix. We get a 3 cross 3 matrix. And this sequence to ABC transform is a very standard transform. So, we are not discussing about it. It is available in any textbook and it is being taught at the very basic level whenever we are talking about the sequence components. So, we know it. So, then therefore, just by applying this particular sequence to ABC transform technique, so from this diagonal matrix we would be able to find out the ABC domain. So, this matrix is in ABC domain. So, this matrix is impedance matrix in ABC domain. So, this is our impedance matrix in the ABC domain, and then this is ABC. Now, we need to understand that the entries of this ABC matrix need not be, or rather basically this particular matrix in the ABC domain need not be a diagonal matrix, although this matrix would be a diagonal matrix, but depending upon the transform, using the transform, this matrix will not be a, in general will not be diagonal matrix. So, it will have its own off diagonal terms and etc., etc. So, everything would be there. Well, so now what happens is that I now have essentially, so after that we do shift the generators here. We say that the internal, so then ultimately, so I have got generators here and generators here. Please note bus number 6, 7 and 8, they are the virtual buses. These buses, they really do not exist inside the generator, but it is our own construction. We assume that instead of the generator feeding power to, at its terminal bus, it is actually feeding power to its internal bus, and the power comes to the terminal bus after traveling through the generator impedance, and that is what we are saying. Essentially also that happens because this generator internally generates some voltage, that voltage actually forces some current, and that current ultimately reaches the generator terminal by traversing through the generator impedance. So, now for this system, so now my unknown quantities are actually, now please note bus 1, 2, 3, 4, 5, these are the original buses. So our so here so now some conventions we will be using. So we will be using some conventions throughout this course. That one is that the M generators are connected at the first M buses of the system. So that means in the original system that means i.e. in the original system M generators are connected at these are our convention. I mean, there is no hard and fast rule, but we shall be working with these conventions because it will make our analysis little easier. Connected at bus number 1, 2 to M. And second convention we will take it is that for generator at bus I I is of course greater than equal to 1 less than M. The internal bus is numbered as n plus I. For example, in this system, originally our generators are connected at bus 1, bus 2, bus 3. So here in this system we said that n is equal to 5. So for bus 1 the corresponding internal bus is 6, which is nothing but 1 plus 5, that is basically 1 plus m. For bus 2 the corresponding internal bus is 7, that is 2 plus 5, that is 2 plus n, and again for bus 3 the corresponding internal bus is 8, that is 3 plus 5. So therefore for any general system, for any generator connected at bus I, the corresponding internal bus would be numbered as n plus I. I should write corresponding. Now, as we discussed earlier, that the original buses are all unbalanced bus. So then therefore here bus 1, bus 2, bus 3, bus 4, these are all unbalanced bus. Now observations. Now we should also some observations. Observations 1 is all original n buses are unbalanced bus. And observation 2 is, which we have already discussed and we have already explained the rationality behind it. The all original internal buses are balanced bus. Now, because this internal buses, so then therefore because these all original n buses are unbalanced bus, so then therefore for every original n bus the unknowns are for every original n buses. So then therefore from there I can write that for every original n bus the unknown quantities are because these are all unbalanced bus. So then therefore the voltage magnitudes as well as the angles for each of these phases A, B, C need to be computed. So then therefore VIA, VIB, VIC as well as theta IA, theta IB, theta IC need to be calculated. So then the unknown quantities are VIA, VIB, VIC and theta IA, theta IB, theta IC, right, where we say that VIP, and we have already said, again we repeat it, that VIP is nothing but voltage magnitude at bus I corresponding to phase P, where I is I is for all n buses and P is A, B, C. Similarly, theta IP also voltage angle at bus I corresponding to phase P, where again this also has got the IS. So that means for n buses, so that means for n original buses, total number of unknown is 6n, because at every bus there is total number of unknown is 6n. So out of this there are 3n number of voltage magnitudes, and this 6n is essentially can be 3n voltage magnitudes basically. And I mean, what are these 3n voltage magnitude? These are nothing but the voltage magnitude at every bus corresponding to every phase, right? And these are 3n voltage angle. right? So I mean, what are these voltage angle? Essentially the voltage angle at every bus at every phase. So then therefore if there are n buses, so then for each bus there are 3 voltage magnitudes corresponding to phase ABC, and for and also there are 3 voltage angles corresponding to phase ABC. Every internal bus is and every internal bus is balanced. Because every internal bus is assumed to be balanced bus, so then therefore what we can, so then therefore for every internal bus, and internal buses are numbered as as essentially n plus 1, n plus 2 dot 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 n plus m, right? For example, in our example it was 6, 7, 8 n plus m. So because every internal bus is actually balanced, so then therefore I can write down that VIA is equal to VIB is equal to VIC, where I is n plus m n plus 1. So that means for every internal bus, n plus 1 I n plus m. What does it mean? That for every internal bus numbered from n plus 1 to n plus m, the voltage magnitudes are equal because these are corresponding to the balanced bus, and theta IB would be taken as theta IA minus 120 degree, and theta IC would be taken as theta IA plus 120 degree. For I, again I n plus m n plus 1. For example, in our case, for bus number 6, 7 and 8, VIA would be equal to VIB would be equal to VIC, and also basically the theta IB would be essentially 120 degree lagging from theta IA, and theta IC would be 120 degree leading that of theta IA, right. So that means for m internal bus, total number of unknown. So then therefore because of this we have to only calculate VIA and theta IA, because once I know VIA I would be able to calculate VIB and VIC, and also once I know theta IA I would be able to calculate theta IB and theta IC. So the total number of unknown is 2 into m for every bus, as for every bus unknown quantities are Via and theta Ia are the only unknown quantities. Right. So then therefore it appears that my total number of unknown is 6n plus 2n. Okay. We will keep on continuing this discussion in the next lecture. Thank you.